Everyone looks at the stock market and assumes the AI scaling race means endless, unbreakable blank checks for Nvidia. But the data points to a massive hidden efficiency shock that could collapse their pricing power. And if that is true, then the entire economic foundation of the AI boom is about to be violently repriced.
Right, and this is a shift that is going to play out over the next 12 to 36 months. We are looking at a fundamental rewiring of the deployment bottleneck.
Yeah.
Right now, capital and power are entirely consolidated around a very specific hardware ecosystem. But when efficiency breaks that bottleneck, power shifts. It shifts to the open source ecosystem. It shifts to agile hardware startups, and it violently shifts away from companies dependent on maintaining 75% gross margins in a hardware market.
So for this deep dive, we are looking at a stack of recent architectural research papers, financial teardowns of NVIDIA's supply chain, and the technical documentation behind DeepSeek's recent breakthrough models. Our mission today is to figure out if the trillion-dollar AI hardware market is built on a foundational illusion. By the end, the important question is not whether AI will change the world, it is whose infrastructure will survive the efficiency collapse.
Exactly. But before we can dismantle the status quo, we really have to establish exactly what the status quo is.
Yeah.
I mean, for the last decade, since around 2012, when AlexNet first proved the raw power of deep learning, we have been operating under what we can call the original scaling law.
Right, the pre-training scaling law. For anyone tracking this space, the playbook has felt, brutally simple.
Yeah.
You take a massive model, you increase the parameter count into the billions and then the trillions, and you just shovel an astronomical amount of capital expenditure into GPUs.
Yep.
And you train that model on trillions of tokens of text. And it worked, right?
It did work. The leading labs could literally predict the benchmark scores of their models before they even finished the training run. You feed the machine more data and more compute, and the machine gets smarter. It was highly predictable.
But that original scaling law has a hard physical limit.
It does. We are slamming into the data wall.
Yeah.
We are effectively exhausting the accumulated high-quality data produced by human history.
I was actually trying to wrap my head around this data wall concept before we recorded, and the sources lay out the math, and it's completely staggering. Take Google Books, for instance.
Right.
They have digitized roughly 40 million books. Now, that feels infinite to a human mind, but if you take a typical book and convert it to AI language, say 65,000 to 130,000 tokens per book, that entire library, arguably the densest collection of human knowledge, tops out at around 5.2 trillion tokens.
Yeah.
Is that really not enough for these models?
It really isn't, and here's why. Frontier models today are already training on corpora of 15 trillion tokens.
Wait, 15 trillion? So where's the rest of that data coming from, if not books?
Well, it comes from scraping the internet. But there is a severe hierarchy of data quality here. If you scrape every academic paper on Archivos V, which is over 2 million highly technical papers, and you add the 3 billion digitized newspaper pages from the Library of Congress, you maybe add another couple trillion tokens of truly high-quality, dense human knowledge.
Okay, so you're still nowhere near 15.
Exactly. After that, you are forced to scrape the bottom of the barrel. You can transcribe every single YouTube video or pull every comment from Reddit, but the quality of that data degrades quickly. A vlog about grocery shopping or a toxic forum thread does not have the same informational density or logical rigor as an organic chemistry textbook.
Right, obviously.
Once you hit about 7 trillion tokens, you have functionally consumed the prime human archive.
Which brings up a wall you can't just throw more money at. You can buy more GPUs, but you can't force humanity to suddenly write 10 trillion more textbooks by next Tuesday.
Exactly. And the industry recognized this data wall. The response has been a massive pivot to a second scaling law, which is inference-time compute. This is the breakthrough driven by chain-of-thought models. You see this in OpenAI's O1 and O3 and DeepSeek's R1.
Okay, let's unpack this, because this is where the physics of the industry fundamentally changed.
Yeah.
In the old paradigm, almost all the compute cost happened up front, right? During training.
Right.
You spend $100 million teaching the model. But once the model was trained, asking it a question, the inference stage, was incredibly cheap and linear. You ask a question, it spits out an answer token by token, but chain of thought completely changes how a model thinks.
It changes the physics of inference entirely. Instead of just answering the user directly, the model generates an internal scratch pad. It produces intermediate logic tokens. It essentially talks to itself in a latent space before it formulates a final output.
But why does talking to itself require so much more compute?
Well, think about how standard models fail. With traditional autoregressive models, if the model starts down a wrong logical path in its first few words, it is trapped. It acts like a child caught in a lie.
Just spinning a yarn to justify the first mistake.
Exactly, because its architecture forces it to remain internally consistent with the tokens it already generated. It can't go backward.
Yeah.
But chain of thought allows the model to test hypotheses, recognize dead ends, backtrack, and verify its own logic. But doing that requires massive amounts of processing power at the exact moment you ask the question.
So it's basically the difference between reading a library and hiring a worker. The original scaling law is like forcing someone to read every book in a library for 10 years so they instantly know the answer to any question you shout at them. But the new inference scaling law is like giving a human worker a complex math problem. If you give them 5 minutes, you get one result. But if you give them 5 hours, they can double-check their math, run simulations, try 3 different formulas, realize Formula 2 was a dead end, and guarantee the right answer. The longer they think, the better the result.
That is the perfect way to visualize it. And this creates an effectively infinite sink for compute. I mean, there is a documented case of OpenAI throwing thousands of dollars of compute at a single, highly complex math problem using this exact method. When you realize that every enterprise query, every coding task, every legal analysis could benefit from this extended thinking time, you see an enormous incentive to deploy hardware at a scale we have never seen.
But this is where the story gets uncomfortable. Because if there's an infinite sink for compute, we have to look at who is collecting the toll on all that processing power. We have to ask why a single company, Nvidia, captures almost the entire profit pool from this compute demand.
Yeah, the anatomy of this monopoly is fascinating, mostly because it defies the historical gravity of the semiconductor industry.
Defies gravity is putting it mildly. Look at the financial teardowns in our sources. Nvidia's valuation briefly surpassed the combined stock markets of England, France, or Germany.
It's wild.
But the metric that really stands out to me is the margin. They command roughly 75% gross margins. To put that in perspective for you, if you look at a highly consolidated semiconductor market like DRAM, where there are basically only 3 massive players, globally gross margins historically average around 20%, Nvidia is operating in a completely different stratosphere. They're charging luxury good markups for industrial hardware.
Right, and the prevailing assumption in the market, and frankly in the media, is that NVIDIA's hardware is just that much better, that they possess some unbreakable monopoly on silicon physics, but the data shows that as a myth.
This was one of the most surprising takeaways for me. I always assumed an NVIDIA H100 was just physically light years ahead of anything else. But the research points to AMD. They manufacture chips with comparable transistor counts using similar advanced fabrication nodes for roughly half the price per FLOP compared to NVIDIA.
Yeah.
The raw processing power is there. The silicon is highly competitive. So why does AMD lose every single time a major tech company writes a check?
Because the bottleneck is not the silicon. The first moat is software, specifically CUDA. It is NVIDIA's proprietary parallel computing platform and programming model.
Let's ground this for a second. What does CUDA actually do? If I'm an engineer, why do I care about CUDA?
Well, a GPU is essentially thousands of tiny processors designed to do basic math at the exact same time. But to get your high-level AI model, say a neural network written in Python, to actually split its workload efficiently across those thousands of tiny processors, you need a translation layer. You need a framework that tells the chip exactly how to manage memory and parallelize the tasks. That is CUDA. NVIDIA launched it in 2006, long before AI was profitable, and they seeded it into every university computer science department.
So it is an entrenched language. When a tech giant hires a machine learning engineer for $650,000 a year, that engineer thinks in CV. They dream in CUDA. The foundational AI libraries, like PyTorch, have been heavily optimized for it over a decade. And if that engineer tries to use AMD hardware,
they hit a wall. AMD's alternative software stack and Linux drivers have a historical reputation for being highly unstable. If you are running a $100 million training run, you cannot afford for your software drivers to crash midway through. You pay the NVIDIA premium for the peace of mind.
So software is moat number 1. But the sources highlight a second moat that feels even more critical for the massive scale we're talking about, and that is the interconnect.
Yeah, in 2019, NVIDIA bought an Israeli company called Mellanox for $6.9 billion. In retrospect, it might be the most important acquisition in the history of AI.
Explain why. If I buy 10,000 GPUs, why do I care so much about the cables connecting them?
Because Training a frontier model isn't about running one chip. It's about wiring tens of thousands of GPUs together into a single massive supercomputer. During a training run, you are moving petabytes of data, the weights and activations of the neural network, across this massive cluster constantly.
Right.
If even one fraction of the network lags, or if data packets drop, thousands of $40,000 GPUs sit completely idle, waiting for data to arrive. Mellanox gave Nvidia InfiniBand the ultimate interconnect technology to guarantee massive, uninterrupted bandwidth across thousands of chips.
So Nvidia doesn't just sell you the engine, they sell you the only transmission system capable of handling the engine's horsepower. And if you buy someone else's transmission, the engine stalls.
Precisely. And this is the vulnerability. If we step back and look at this as a system, Nvidia's moat relies entirely on artificial bottlenecks. It relies on software lock-in and interconnect friction. And if there is one constant in the history of capital markets, it is that markets view artificial bottlenecks as damage, and they aggressively route around them.
Which brings us to the physical attacks on Nvidia's interconnect moat, the hardware insurgency. If wiring thousands of chips together is the core friction point, some companies are just refusing to play that game entirely. Let's look at Cerebras. They built something called the wafer scale engine, the WSE3. I saw the photos of this thing in the research, and it looks absurd.
The scale of this architecture is hard to overstate. A standard Nvidia H100 chip, which is the workhorse of the AI industry, has a die area of 814 square millimeters. It fits in the palm of your hand.
Okay.
The Cerebras chip is 46,225 square millimeters. It is 57 times larger. It takes up the entire uncut silicon wafer.
Wait, I need to stop you there. Because anyone who knows even a little about semiconductor manufacturing knows you don't just print a chip the size of a dinner plate. Normally, you take a big circular wafer of silicon, you print hundreds of little chips on it, and you slice them up. You do that because there are always microscopic defects in the silicon, and if one little chip has a defect, you throw it away and keep the rest. If Cerebras is using the whole wafer as one single chip, how do they deal with defects? Doesn't a single microscopic flaw ruin the whole dinner plate?
That was the exact engineering hurdle that kept the rest of the industry from attempting this. Cerebras solved it by building extreme redundancy into the wafer. If one section of the wafer has a manufacturing defect, the hardware is designed to automatically route around the dead zone. But the payoff for solving this is massive.
The payoff is that it completely bypasses Nvidia's Mellanox moat. The WSE3 has 900,000 cores. By putting everything on one giant chip, the interprocessor bandwidth issues just vanish. You don't need complex networking cables, optical transceivers, InfiniBand switches to connect 1,000 tiny chips together if your one massive chip does the work of 1,000 chips. The data never has to leave the silicon.
And the result of that localized data movement is blistering speed. The Cerebras system can generate roughly 1,500 tokens per second. For context, the standard ChatGPT interface you use on your phone generates fewer than 30 tokens per second.
That is a staggering jump in capability. But Cerebras isn't the only one taking a totally different approach to the physics of AI compute. There is also Groq. They are attacking the problem through something called deterministic compute.
Right. Instead of using a traditional GPU, Groq built a tensor processing unit, or TPU. Now, this requires a slight mental shift. A GPU is designed to be highly flexible. It has a complex hardware scheduler that is constantly juggling tasks, deciding which core should handle which calculation in real time. But that flexibility creates tiny, unpredictable delays.
Right, because the hardware is constantly thinking about how to do the work rather than just doing it.
Exactly. Groq realized that deep learning math is actually highly predictable. You know exactly what matrix multiplications need to happen in what order. So they stripped out the complex hardware scheduler entirely. Their architecture is perfectly deterministic. The exact timing of every single mathematical operation is known before the code even runs.
What does that mean in practice?
It means they can optimize the software at the compiler level in ways that are impossible on a GPU. The compiler orchestrates the flow of data across the chip like a perfectly timed symphony. No core is ever waiting, no memory is ever queried late. The result is inference speeds of over 1,300 tokens per second, rivaling Cerebras, but using a completely different architectural philosophy.
So we have these agile startups building radically different physical machines, but it isn't just startups. The hyperscalers, the cloud giants who are Nvidia's own biggest customers, are actively building the weapons to destroy Nvidia's margins. Google is already on the sixth generation of their custom TPU. Amazon has their Trainium 2 and Inferentia 2 chips, and the sources note they are currently building a massive 400,000 chip cluster specifically for Anthropic.
Yep.
Microsoft is building custom silicon. Apple has been designing world-class neural processors for their phones and laptops for years.
This is the part most companies, and certainly most retail investors, are entirely missing. We have to look at the TSMC reality. Nvidia does not physically manufacture their own chips. They do not own factories. They are an intellectual property company. The actual physical foundries belong to a Taiwanese company, TSMC, using incredibly complex lithography machines from a Dutch company, ASML.
So I have to push back here because this feels like the Achilles heel of the entire trillion-dollar narrative. If every major customer, Google, Amazon, Microsoft, Apple, is heavily investing in designing their own custom chips, and TSMC is the actual factory that will print chips for anyone who shows up with a big enough check, isn't Nvidia essentially just a design firm collecting a 90% luxury tax on top of TSMC's labor?
That is exactly the fragility of their hardware position. TSMC is politically and economically incentivized to fabricate chips for anyone. If you are Amazon and you have the capital to hire away a dozen top silicon engineers from Nvidia or AMD, you can design your own chip.
Yeah.
Now, your first-generation chip might only be 50% as efficient as a bleeding-edge Nvidia H100.
But if you are building it at cost...
Exactly. If you're building it at cost, without paying NVIDIA's massive 75% gross margin, the economics still heavily favor the custom silicon. You can just print twice as many of your own chips, achieve the same compute power, and still save billions of dollars in capital expenditure.
But wait, earlier you said the hardware doesn't matter if the software is locked into CUDA. You said the trillion-dollar tech giants are stuck because all the engineers and all the code are deeply embedded in NVIDIA's software ecosystem. If Amazon prints 1 million Trainium chips, how do they get the CUDA-trained engineers to actually use them?
That sounds like a technical detail. It is not. The unbundling of the software is the second front of this insurgency. Because just as capital routes around hardware bottlenecks, human ingenuity routes around software lock-in.
And this brings us to what is happening right now in the open source community. Let's look at what is happening to AMD. We established they have historically struggled because of poor drivers, effectively ceding the AI market to Nvidia. But agile hackers are stepping in where corporate AMD failed.
Right. The story of George Hortz is the perfect example of this dynamic.
Right. The hacker who originally jailbroke the iPhone and the PlayStation. He got tired of AMD's unreliable drivers crashing his AI hardware setups. So rather than giving up and buying Nvidia, he is writing his own RDNA 3 assembler. The sources highlight that in roughly 12,000 lines of code, he is building a sovereign, custom driver stack from scratch. He is single-handedly trying to make cheap, consumer-grade AMD chips viable for heavy AI workloads.
But it goes much deeper than just fixing AMD's driver problem. The real existential threat to NVIDIA's software moat is the rise of high-level abstractions. We are looking at frameworks like Apple's MLX, OpenAI's Triton, and Google's JX.
Break those down for me. What does a high-level abstraction actually do in this context?
These frameworks allow machine learning developers to write their code once, at a high level of abstraction, meaning in simple mathematical Python, without ever thinking about the specific hardware underneath. You just write the logic of the neural network. Then, the system's compiler takes that high-level code and automatically translates it to run perfectly on whatever hardware you happen to be using, whether that is an NVIDIA GPU, an Apple M3 chip, or a Google TPU.
Okay, let's use the assembly language analogy because that made this instantly click for me. In the 1980s, the best, fastest software in the world programs like PKZIP or the original WordStar were handwritten in assembly language by absolute wizards.
Yep.
To write in assembly, you had to know the exact physical architecture of the specific CPU you were programming for. You were manually moving data between physical registers. If you wrote a program in a higher level, easier language like C, it was considered too slow and bloated. But over time, C compilers got better.
They got so good that the automated compiler could eventually optimize code better than a human handwriting assembly. Today, virtually nobody writes an assembly language for commercial software. The automated translation layer won.
CUDA is becoming the new assembly language. Right now, tech companies pay a premium for engineers who can hand-tune CUDA code to squeeze every ounce of performance out of an NVIDIA chip. But the compilers underneath Triton and JIX are catching up. When Triton can take a standard neural network and compile code that runs 95% as efficiently on a custom Amazon Trainium chip as it does on an Nvidia GPU, the CUDA lock-in evaporates. The developer doesn't need to know CUDA anymore.
And here's where the convergence becomes truly dangerous for incumbents. We're rapidly moving toward LLM-driven translation. Very soon, an AI reasoning model will be able to take a massive algorithm written in legacy CUDA and port it perfectly, line by line, to the native machine code of a Cerebras wafer or a Google TPU.
So the software moat is literally being attacked by the very AI models that the hardware was built to train. That is incredible.
Right, so we have established the hardware threats. Startups are changing the physical shapes of chips, and hyperscalers are printing their own. We have established the software threats. Abstraction layers are deleting the need for CUDA. But the obvious conclusion is wrong.
The obvious conclusion being that Nvidia just slowly loses market share to cheaper competitors over the next decade.
Right. The real threat is not just that someone will build a cheaper GPU. The ultimate threat is the sudden, violent collapse of aggregate compute demand. And that creates a very different kind of risk.
Which brings us to the DeepSeek shockwave. This is the efficiency miracle that the mainstream media is completely failing to understand. If you take away anything from this deep dive, it should be the implications of what this one startup just pulled off.
Let's set the stage.
Yeah.
You have a relatively obscure Chinese startup, fewer than 200 employees. They came out of a quantitative hedge fund background, which is a crucial detail regarding how they approach resource constraints. And in late 2024 and early 2025, they released two models, DeepSeek V3 and DeepSeek R1.
And let's be clear. These aren't toy models or scaled-down academic experiments. They rival OpenAI's O1 and Anthropic's Claude 3.5 Sonnet on major benchmarks. They are absolute frontier-class intelligence. But here is the shock, and the number that should terrify the hardware market. They trained the V3 model for approximately $5.5 million.
To put that in context, Western labs are routinely spending well over $100 million per training run. Rumors suggest some upcoming models might push toward $1 billion in compute costs. DeepSeek achieved frontier performance while being roughly 45 times more efficient with their capital and compute. And it is vital to understand, they didn't do this by stealing compute or hoarding a secret mountain of GPUs or using stolen data. They did it through intense, unprecedented architectural elegance.
I want to spend a significant time unpacking the technical details of how you cut costs by 45 times, because it is an absolute masterclass in optimization. Let's start with detail number one, FP8 training. What is this, and why does it save so much money?
So FP8 refers to 8-bit floating point precision. This is about how the computer stores numbers in its memory. Most Western labs historically train their massive models in 32-bit or 16-bit precision, which means they use highly detailed, long numbers to represent the weights in the neural network.
Because more detail means a smarter model, presumably.
That was the assumption. The problem is that 32-bit numbers take up an enormous amount of physical memory space on the GPU. DeepSeek built a mixed precision framework that trains the model natively in 8-bit precision. They use much shorter numbers. By doing this, they radically slash the memory requirement per GPU.
Less memory required means you can fit more of the model on fewer chips. So you radically reduce the number of GPUs you have to rent. But how did they not ruin the model? If you chop off the decimal points of all the math, shouldn't the neural network lose its neurons?
That is the genius of their specific framework. They figured out exactly when to use 8-bit precision for the heavy bulk math and when to selectively use higher precision for the sensitive parts of the network that actually require it. They managed the noise perfectly.
Okay, so they shrank the memory footprint with the math itself. The second detail the sources highlight is something called multi-head latent attention, or MLA. The research says this compresses the KV cache. Again, let's ground this. What actually is a KV cache? If I'm asking a model to write an essay for me, what is the KV cache physically doing in the GPU at that exact second?
Well, KV stands for key value. In a standard transformer model, which is the architecture behind almost all modern AI, the model needs a short-term memory to keep track of the context of the conversation. As it reads your prompt and starts writing the essay, it stores mathematical representations of every previous word in the KV cache. This prevents it from losing the plot.
So it's the model's scratch pad of what has already happened.
Exactly. But as the conversation gets longer, that KV cache grows massive. It consumes a huge amount of video RAM on the GPU. During inference, you often run out of memory to store the context before you run out of processing power to do the math.
So how did DeepSeek fix it with MLA?
DeepSeek found a way to compress that KV cache directly inside the training pipeline into a latent space. They drastically shrank the size of the short-term memory footprint.
Yeah.
But what is truly brilliant is that this compression acts as a regularizer. Because the model has less space to store context, it is forced to focus only on the actual meaningful signal in the data, rather than memorizing random noise. It made the model cheaper to run and smarter.
That is elegant. Detail number 3 is multi-token prediction. Usually, these models predict one single token at a time. It guesses a word, looks at it, guesses the next word, looks at it. DeepSeek structurally changed the architecture to predict multiple tokens at once.
Yes, they altered the causal chain. By guessing multiple future tokens simultaneously and maintaining an 85 to 90% accuracy rate on those parallel guesses, they effectively double the inference speed of the model without requiring faster chips.
But the most crucial detail, the one that completely rewrites the hardware economics, is their implementation of a mixture of experts or Moat architecture. DeepSeek V3 is a massive model. It has 671 billion parameters. But the data shows that only 37 billion of those parameters are active during any given generation.
This is the architectural choice that breaks the Nvidia demand thesis. I want you to explain the hospital analogy you brought up earlier because it perfectly illustrates why Moat is so devastating to hardware margins.
Right. I like to think of a dense neural network, the old way of building models, like a massive hospital where every single doctor must consult on every single patient. If you have a hospital with 671 doctors representing every possible medical specialty and a patient walks in with a broken arm, well, in a dense model, you drag all 671 doctors into the emergency room to look at the arm. The podiatrist, the brain surgeon, the cardiologist, they all have to process the data. It is massively inefficient and requires a giant room or a giant GPU cluster to hold them all.
And how does mixture of experts change the triage?
In Moat, you have a highly intelligent triage nurse at the front door. This is the router mechanism in the neural network. The patient walks in, the triage nurse instantly recognizes it's a bone problem, and instead of calling the whole hospital, the nurse only calls the 37 bone specialists. The other hundreds of doctors stay asleep. Because you're only activating a tiny fraction of the network at once, the specific experts needed for that exact token, the compute cost plummets.
The physical result of this is that this massive frontier-class model can run locally on 2 consumer-grade Nvidia 4090 GPUs.
That is the part that blows my mind. We are talking about under $4,000 of retail gaming hardware sitting under a desk, replacing the need for massive multi-million-dollar clusters of H100s for inference tasks.
DeepSeek proved that the bottleneck is not the model. It is the system around the model. And they took this philosophy even further with their reasoning model, DeepSeek R1.
All right, V3 was about pure efficiency, but R1 was about autonomous reasoning. The documentation details how they developed R10 using pure reinforcement learning without relying on massive, perfectly curated, supervised datasets.
This completely upends the Western playbook. The industry assumption was always that to teach a model to reason, to do complex math or code, you needed human experts to manually write out thousands of examples of perfect step-by-step logic. You needed supervised fine-tuning. It is incredibly expensive and slow. DeepSeek bypassed the humans. They used a rule-based reward system.
Meaning what? How do you reward a model without a human grading it?
Instead of training a complex secondary neural network to judge the model's outputs, which often leads to the model reward hacking or tricking the judge, they just gave the model objective tasks, like math equations or code compilation. They mathematically rewarded the model for one thing, getting the right answer in the correct format. Then they just let it play out over millions of iterations.
And during this pure reinforcement learning process, the researchers witnessed what they called an aha moment. The model spontaneously learned to revise its own thinking midstream. It would start solving a math problem, realize it was making a logical mistake, output a token flagging its own uncertainty, and try a completely different approach. This wasn't explicitly programmed into the code by humans. It was a pure emergent behavior of the reinforcement learning process.
The results of this architectural elegance are undeniable. On the AIM 2024 math competition, which is a brutally difficult benchmark, R1 scored 79.8% accuracy. On the Math 500 benchmark, it hit 97.3%. And then they did something that should terrify every hardware incumbent. They distilled this genius-level reasoning down.
Right, distillation. They took the outputs of the massive R1 model and used them to train tiny 14 billion and 32 billion parameter models. And those tiny, hyper-efficient models easily outperform dense models 5 times their size.
So what does this reveal? It reveals that parameter count is vanity and training architecture is sanity. The entire Western AI industry might be massively over-provisioning compute to brute force a problem that a tiny team of quants in China just solved with architectural elegance.
Which brings us to the reflexivity of the market and the second-order consequences. We have spent this time unpacking the technical realities, wafer-scale chips, software abstraction, 8-bit precision, and mixture of experts. Now we have to connect all of these technical threads back to the stakes we established at the beginning. We have to look at capital and power.
The organizational crisis this creates within Western tech giants is profound. You cannot overstate the internal panic.
I mean, there's a rumor going around Silicon Valley right now that 13 senior engineers on Meta's Llama team earn more in total compensation than what DeepSeek spent to train their entire V3 model. Whether that exact math holds up or not, the directional truth is devastating. If you are Mark Zuckerberg or Sundar Pichai, how do you justify to your board buying 100,000 H100 GPUs when a startup just proved that 2,000 GPUs, architected intelligently, is enough to build a frontier model?
You can't, and it immediately triggers a price war at the deployment layer. DeepSeek is currently charging up to 95% less for API access than its Western competitors. When intelligence becomes that cheap to produce and serve, margin compression sweeps across the entire industry ecosystem. You cannot charge a premium for AI wrappers or basic enterprise AI tools when the underlying intelligence costs fractions of a cent.
And that exposes Nvidia's extreme fragility. If you look at their valuation, their stock is trading at roughly 20 times forward sales. That valuation does not price in a steady state. It inherently requires continuous exponential growth in aggregate demand for GPUs. The market assumes the hyperscalers will just buy more and more hardware forever. But what happens to that aggregate demand when a startup proves you can achieve a 45 times efficiency gain on the software layer? What happens to Nvidia's stock when those 75% gross margins start slipping to 70% and then 60% because Amazon refuses to pay the premium?
The market is currently pricing in a reality where the bottleneck remains silicon. But the 5 vectors of attack we just explored, architectural innovation like Moat, vertical integration by hyperscalers printing their own chips, software abstraction layers deleting CUDA, inference efficiency breakthroughs, and TSMC's democratization of manufacturing, make that narrative highly reflexive and deeply fragile. When you look at the systems level shift, it becomes clear that artificial moats cannot withstand the sheer force of this much capital and intellect-seeking optimization.
So here is the real question for you to weigh in on. What breaks first? Nvidia's 75% gross margins, the CUDA software monopoly, or the massive capex budgets of their hyperscaler customers?
The pressures are converging simultaneously. Hyperscalers are realizing they don't need to spend the capex if the software abstractions allow them to use cheaper, vertically integrated hardware, which directly attacks the CUDA monopoly, which ultimately collapses the 75% margin.
Most people are watching the model leaderboard. The real leaderboard is infrastructure, deployment, and organizational adaptation. The AI race will not be won by the companies with the largest pile of expensive GPUs. It will be won by the systems that rebuild themselves fast enough to operate without them.